Here's a couple theorems about vector spaces. One of them is in the book and one of them is not. So let's suppose we got a vector space V, and let U be any element of V and let K be any scalar. Of course, by scalars, for this course, we mean real numbers, which is why we call them real vector spaces, because the scalars we're multiplying by are realers. Try that again. The scalars we're multiplying by are real numbers. There's also such things as complex vector spaces where your scalars are complex numbers, or any other. There's a lot of different types of vector spaces depending on what your scalars look like. For this course, we're talking real numbers. Okay? The vectors may be anything. It might be elephants or whatnot, but at least we're multiplying by real numbers. So here's the situation. In any vector space, it turns out that 0 times any vector is always the 0 vector. Remember, the 0 vector is the additive identity. And then any real number k times the 0 vector is the 0 vector. -1 times the vector is the additive inverse of that vector, which we're calling negative u or minus u. And if k times u equals the 0 vector, then either k equals the number 0 or u is the 0 vector. Okay. Let's prove part A on that. It turns out C is in the book, and B and, well, A is in the book too, but I'll walk you through A. C is also in the book. B and D are left as exercises, and we'll probably do those maybe in class or something. Or you can try them on your own. So here's the proof of part A. Notice that that 0u plus 0u is equal to this. This is axiom A. This is distributive property. That you have real number addition here times this, as there's a scalar times u, and there's a distributive property that works this way. But in real numbers, 0 plus 0 is 0, so this plus that is equal to this again. Now, we know that every vector has an additive inverse. So in particular, whatever this vector 0u is, it has an additive inverse, which we call minus 0u, right? Minus whatever that is. So if I add this vector to both sides of that equation, I've got the left-hand side plus minus 0u, and I've got the right-hand side here plus minus 0u. And now I'm going to use an associative property here to regroup this side this way. So move the parentheses to here. Left that side alone. Notice that inside the parentheses, this is 0u plus negative 0u. That should be a vector, which is 0. And likewise here, this is 0u plus negative 0u. So that's u. That's axiom 5. That is, a vector plus its additive inverse is the 0 vector. And then I'm going to say, oh, but 0u plus 0 is just 0u. That's axiom 4. That's what the 0 vector does. And so I have that 0u is equal to the 0 vector. Okay. You might imagine that part B of that theorem is similar, but I'll let you see if you can prove B, C, and D. Okay. I want to point out another theorem that is not in the book, but this is partly why, well, the theorem we just looked at and this theorem here, it's like, why do we even have this notion? It's, well, anything that satisfies those first 10 axioms also satisfies these 4 things, right, that we just did here. I didn't have to list these as axioms, I just have to prove them. If I've got the other 10, I've got these 4. If I've got the other 10 and those 4, then I've also got this theorem here, it turns out. So here's my theorem. I'm going to claim that there's only one 0 vector in V, and each element has only one additive inverse. So to prove that, let's part 1 or A, whatever. A is 1, B is 2. So suppose that I have 2 elements in the vector space here, such that they both act like zeros. Okay, so I want that u plus A equals u for all u, and u plus B equals u for all u. So both of these are behaving just like the additive identity. So they're both what we would call a 0. Now, take a look at A plus B. I think I have this backwards. A plus B, according to this up here, U plus A, or U plus B is always equal to U. So this should be equal to A right here. But A plus B, if you turn it around, is B plus A. Well, anything plus A is that anything, so this must be a B. So I have A plus B equals A, I have A plus B equals B, so A equals B. If I have two things that are acting like zero, they're both the same thing. I have only one additive identity. I have only one zero element. Okay, now let's suppose I've got, for the second part there, let's suppose I've got two vectors that both think they're the additive inverse of this particular vector u. So a plus u is equal to 0 and b plus u is equal to 0. Okay? So I know that a plus u is equal to b plus u because, well, they're both equal to the 0 element. Now, u has an additive inverse. There is a negative u. And so let me add that to both sides. Do a little regrouping here using the associative property. That is axiom 3. And then I have that this is equal to 0 and this sum right here is equal to 0. That's axiom 4 or 5, 4, I think. 5. And then, well, a plus 0 equals a, and b plus 0 equals b. That's axiom 4. Right? And so a equals b. If you have two things that both think they're the additive inverse of some particular vector, then they're both the same thing, and hence there is only one additive inverse of the vector u. Okay. These are things that are true about any of those vector spaces that we talked about in the previous video, or any vector space that we're going to talk about in the future. All of this stuff in this video is based on the 10 axioms that you assume are true once you're in a vector space.